Hello. Lab 5, Potential and Kinetic Energy Transformation. Energy is motion in different forms, okay, all kind of form. So far we have learned kinetic energy, which is half mass times velocity squared. And in this lab, we are introduced to two different more type of energies, namely potential energy and thermal energy. Yes, energy has many forms: kinetic, potential, thermal, electrical, and nuclei. Energy can never be created nor destroyed. This is so-called law of energy conservation. Yet they can transfer from one place to another, or they can transform from one form to another form. In this lab, students explore transformations between kinetic, potential, and thermal energies. In this skate park simulation, this is a skating park, and in this simulation, a skater is put at some height. You will start this simulation by click this link. Is another Fiat simulations. In this simulation, skater can be put at a parabolic track like this. And if you put it at a certain height, and which can be measured with a tape measure provided, also simulated in here, and then you let go of this skater, it will swing down, and then it will slide up, and then fall back down again, and it will swing back and forth like this. And so when it is in motion, that's the kinetic energy. And when it is at a certain height, that's the new concept for you, is the potential energy. Okay, the potential energy is related to the position of an object around the Earth or planet. When we are dealing with the problem near the Earth's surface, the potential energy can be approximately expressed in a mass, gravity, h, or simply called mgh. If you do physics a lot, and then simply mgh is the potential energy. Here, mass is obviously the mass, and g is 9.8, and then h is the height, which means the higher the object, the higher its potential energy. The higher the object, the higher its potential energy. So, potential energy is energy. Once again, the concept of energy is how much potentially it can do work, or can transform this energy into other form of energy. So here, the energy of potential energy is due to gravity is m times g times h. That's the height. Okay, and also thermal energy, we talked about briefly. It is invisible, but one can feel it, and if something gets hot and warm. And it is actually due to the motion of microscopic particles, their shapes, and the relative positions. They are in motion, even though you cannot see. You can think about thermal energy as how vigorous the atoms and molecules are moving inside the bulk material. The goal of this lab is basically demonstrate the conservation law of energy, which means the energy can never be created nor destroyed, but they can transform from one form to another. In other words, if a kinetic energy is lost, there must be some other form of energy that's increased or gained. Okay, and this is the system like skater park, and that's what we want to explore. Now, if you click this link, it will take you to this website here. Now, and then we actually do two experiments. One, and we were doing, and we'll see. First, you play with it. So you can put a skater here at a certain height, and you let go, and it will slide down, and so on. So when it's getting faster, the kinetic energy is being calculated over here, and also the potential energy, simply the height times mass times the height, g. Since g and mass are both constant, the potential energy basically related to the height of the girl here. Okay, and so then now we can also change here the friction on this. So friction is the mechanism that resists the motion, is between two surfaces, and the friction will be the factor that transforms the kinetic energy into thermal energy. The actual what's happening is it rubs the surface, make the molecules move harder, and at the same time the kinetic energy is lost at the same time, but the energy never goes away, and the molecules or tiny particles in the material on the track or on the wheel are getting mobilized and getting moving faster, so they become hotter. So that's in the form of the thermal energy. So you can adjust how much friction is there. So if there's see, you can have a lot of friction in this case. You let it go, so it just swing a couple of times, right? Okay, and you have less friction if you put over here, or swing more times. And if you have, if you have, say, no friction, and I will let you play with it. No friction, and if you go, swing longer time. Of course, you can also adjust the gravity level, simulating that you are on other planets or so on. So we do the experiment, we set the mass of the girl at a certain level, and we will use this for another lab later on when we talk about energy transformation or energy conservation. But this first lab, we just want to basically see this idea. So friction level can be adjusted, and also the height. So this is a tape measure. You do two experiments, and then you do first experiment, you let it go from 4 meters. So you set at 4 meters. All right, so, and then stop this, and you put this at 4 meters. You go by this red dot. Okay, and then start. And then the total energy is calculated over here. You measure the energy level by using this tape measure. I will explain why we use how much energy is there, because potential energy is measured proportional to the height. But then, in fact, any energy can be measured on the same scale. We simply use the meter to measure energy. But although that's not correct, but here, since it's proportional, and it's even though the unit is not perfect, but then we just measure the energy with meters. Put this. So these are the energy. See if you do the simulation, and you see when it's moving, the kinetic energy and potential energy both are changing in real time. Okay, if you don't like the pie chart, you can click here. So the pie chart will disappear. It only sees energy bar. Okay, actually whatever you see in the total energy is never changed. So when the kinetic energy goes up, the potential energy will go down, and vice versa. But in any moment, potential energy, see if you stop this, and at some moment, boom. You see, if you measure this, so if this is 2 meters, that's about 1.9, but then that is 0.1. So then if you go a little more, okay, if you stop a little bit here, so then anytime potential energy, and which is height, and kinetic energy, which is half mv squared, and when you add these two together, they always add up to this total energy. Okay, so that is the energy conservation. So that's with no friction. And now if you turn more, a little bit of friction, you will have one more factor. So then there will be another thermal energy, the hot. So you do the same situation, but because the friction, the energy is never totally lost, but changed to other form. In the end, it changes to the thermal energy. So if you do that, it will stop, and everything becomes, the thermal energy will be total energy, but that's the total energy to begin with, and never lost. So then we just do this measurement. So what actually you do, so you play with this, you can adjust frictions, you can adjust starting height using these meters. Yeah, you go by these red dots, and then you do two simulations. Okay, of course, I always put everything to do. First one, start from 4 meter high and 60 gram and gravity in the medium, and then do this. Then do this exercise, and then you basically I want you to count the number of swings. Okay, how many it can swing and stop. For example, actually I want you to do is to do this. So for example, if you set it here, how many times it swings? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so now if you have less friction, okay, again from 2, guess how many? So that's common sense, right? Okay, go. So that's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 18, 20, 21, 22, 23, 24, 25. Okay, you know what I mean. Maybe go up to 30, right? So we left, so that's what I'm going to count, how many times swings. So you go into here, number of swings, and maximum energy is recorded right here. So maximum total energy measured with the tape. So what is tape? So that's how you want to measure maximum energy. In this case, so 1.9, and so on. So then you enter here maximum kinetic energy, maximum potential energy, and total energy, and you put in this table. And then with lots of potential, lots of frictions, you just go off friction all the way to the top. Okay, and less friction, you put it in the middle half, and no friction, you put it in none. So we have to do this 3 cases. Okay, I don't want you to do a whole lot of this, but so you do 3 cases, and under these questions, I have, for this question, I think I explained for frictionless simulation, what is the potential energy level at the moment when the kinetic energy is a quarter of the total energy. And only this one is a little bit challenging. I want you to observe, not just, so if you start simulation, it keep on swaying, you see all these energy are changing like crazy in real time, and then what you really want to do is observe when this is at a quarter of the total, and what is the potential energy. So where is the potential energy? So then that one you have to just observe. Don't ask me for the answer, okay? And that's the part of the lab, okay? And so then if you put at 4, for example, and so you say, well, go. You try to stop this kinetic energy at a quarter of the total. Try to do that. No, that's half. Okay, maybe. Okay, so if you think about the quarter of the total, and then that about 5.3 or, and what is that? So when the quarter of total is, so kinetic energy was here, and that moment where is the potential energy? And I will ask you a question about that. And that actually, oh yeah, I should move this a little bit the other way. When energy is at a quarter of the distance. For this question A, frictionless simulation, what is the potential energy level? At the moment, the kinetic energy is a quarter of the total energy. For this one, you really have to closely observe. See, when it is swing like this, both potential energy and the kinetic energy are moving. So you will see that when the green move to a quarter of this distance, where that moment, where is the blue? So when this is that kinetic quarter, where is that? But for the frictionless case, okay, I will not show it here, but you will do the experiment for the frictionless case, and then see answer that question. And the rest of the question are very similar, very simple. I will, if you get stuck, let me know. But I don't want to give out the answers at this moment. All right, so they do one case like this, and then you do another case, basically the same thing, but start at 2 meters high and do the same thing over again. And here are some other more questions, illustrate the law of energy conservation, and basically the simple concept. We will talk about this in the class one more again, and then this is the time that we do the lab first, and then do the lecture of the same contents later, second. All right, hope this helps, and if you have questions, you can always contact me, and we can resolve any question you have. Okay, bye-bye for now.